Okay, so let's start. Today, Tudor Padurariu from the University of Bonn will give his third lecture on BPS cohomology and quasi-BPS categories. Tudor, please.
Yes, thank you. Yeah, so yesterday we stopped when at the chi-independence phenomenon. So we said that this is a conjecture of Toda that the BPS cohomologies of moduli spaces of sheaves supported on curves on Calabi-Yau threefolds do not depend on the Euler characteristic of that we choose in these modular spaces. So this is wide open, but one can try to prove it maybe in some for some more classical cohomology theories for which dimensional reduction is available. And one such situation is when we work with a local curve. We have C as more projective curve, L a line bundle, and when we consider the local Calabi-Yau threefold Y, which is the total space of L plus L inverse times omega over our curve C. So if the degree of L is greater than the degree of the canonical divisor, so if this stacks of semi-stable Higgs bundles L twisted are smooth, then this chi-independence is a theorem of Maulik and Chen. And the proof went, actually, so the proof uses the map to the Hitchin base and the fact that in the BBDG decomposition for this particular, so for the push forward along the map from Higgs to the Hitchin base of the IC sheaf on the good moduli space of semi-stable L-twisted Higgs bundles, all the supports are full. So all the supports intersect the open locus of smooth spectral curves.
Is there a filtration on the intersection cohomology of this direct image? So it's perverse filtration or what?
Yes. And also, so the push forward of this also has a perverse filtration. So the intersection cohomologies of both sides will carry perverse filtration. And this isomorphism respects the perverse filtration.
Hesitate to ask how general is this phenomenon.
You mean in the setting of chi-independence or
No.
in the setting of...
Just for the existence of perverse filtration in the for like for two Calabi-Yaus, which mean that zero shifted stacks, symplectic stacks. Yeah.
Yes, I think, the existence of perverse filtration, I believe it's very general because the push forward is a complex of constructible sheaves, and then there you consider the perverse T structure.
Yeah, probably I did not
And
formulate it
and the
properly.
splitting, if you want the splitting, then you want the perverse filtration to split, then there are some results of Davison in this direction.
Yeah, I think we heard his talk about some generalization of this P equal W for stacks. Yeah.
Yes,
Okay.
yes.
Mm-hmm.
But in this case, this are good moduli spaces of smooth stacks. So anyway, so here I'm just using the usual BBDG decomposition. What about usual Higgs bundles where L is the canonical on C? Then we actually need to use BPS when there are strictly semi-stable sheaves. So one may ask, well, is there a version where we still put intersection cohomology? That's false. So the correct version that gives you an isomorphism for all other characteristics, chi, is using BPS cohomology, and it is a theorem of Kinjo-Koseki. So I should say here that
Sorry,
Yes.
just to understand. So your BPS sheaf is a direct image of the IC on the stack itself, but stack is no longer smooth, yeah? Or what?
Yes, that's right.
And basically, in this case, image or direct image of the IC sheaf is no longer an IC sheaf, which
Yeah,
different.
so yeah, so
And so this is why you use BPS cohomology, cohomology and coefficients in this direct image. Yeah.
yes, that's the rough idea. But I think here I should say that kind of this BPS shift in the zero shifted symplectic case, it's more difficult because we define it indirectly through the -1 shifted symplectic space. So
Mm-hmm.
actually, it is the case that the BPS shift also so this is in the zero symplectic case, it is a direct summand of the push forward of the good moduli space map from the stack, zero shifted symplectic stack to its good moduli space. But one does not take IC shift, one takes the dualizing shift. And then takes push forward and then takes first filtration.
Mm-hmm.
Anyway, but it is not the zero locus. Yes, sorry, it is not the full zero perverse cohomology. It's just a sum.
Okay.
I think it is. Yeah, I think it's. I think it will be ideal to also have other descriptions of the BPS shift. Indeed, because the BPS shift in the zero shifted case, it's kind of indirectly defined.
Yeah, sure. Yeah. Okay. Okay.
So Kinjo Koseki. So maybe one comment. This is a classical result. If chi and chi prime are coprime to the rank, then BPS is just the usual singular cohomology, and it says that there is an isomorphism between Higgs GLR chi semistable and chi prime semistable if chi and chi prime are coprime to R. But this follows from non-abelian Hodge theory because both these cohomologies will be isomorphic to cohomologies of twisted character varieties for chi, for the chi power of a primitive R root of unity and chi prime power. But the point of this result is that there is a uniform theory, uniform sheaf that works for all degrees. So just a comment about the proof. So it has to use the T star -1 space. That is, it actually has to use the Calabi-Yau threefold. And the kind of main idea, so we know that moduli spaces of semistable sheaves on Calabi-Yau threefolds are locally critical loci, but they manage, in this particular case of this local curve, to write this moduli space of semistable sheaves globally as a critical locus. So this is the main idea and main innovation. And then they basically reduce it to the Maulich-Shen approach, Maulich-Shen statement, not the kind of global statement here, but the relative statement. The relative statement over the Hitchin base. So they reduce it to.
So in what case it's a global critical locus?
Yes. It's
in what case?
I think I'd say it's I'm almost never. I cannot give you more examples.
Yeah, I
I think it's
understand
kind
that
of a miracle that
for all
happened here.
toric Calabi-Yaus.
Yes, sure, toric,
Yeah,
yes.
that's true.
Toric
Okay.
Calabi-Yau, sure. But I think here is kind of, well, at least for me, it was a surprise.
Okay. Okay.
But it works.
Okay.
So then they reduce it to this kind of relative statement of Maulich-Shen, and they put a vanishing cycle sheet in here. But for example, it doesn't work for moduli of semi-stable sheaves on K3 sets. I mean, that's not, as far as we know, like critical locus, global critical locus. So this is the Kinjo-Koseki theorem. So I should say that there are several other conjectures that are in spirit. maybe not only in spirit, related to this kind dependence conjecture of Knobu. So one conjecture that we propose in our paper, and yeah, inspired, of course, by this Kinjo-Koseki theorem, is maybe I should say that kind of once we have Higgs, or alternatively sheaves on curves in a local sheaf supported on curve in a local curve, there are two directions to generalize, two directions to look for more general phenomena. One is for more general Calabi-Yau threefolds, but the other one is to change the group. So instead of looking at GLR Higgs, consider G Higgs for G reductive group. In this direction, conjecture that generalizes Kinjo-Koseki to general groups says that the BPS cohomology of the good moduli space of the loop stack of semistable Higgs G is isomorphic to the version for the LG, for the dual group. And this is also related to the Hauser-Thaddeus conjecture for SL-PGL duality. And here, yet another conjecture of Safronov is that if one considers the stack of G-local systems on a real-oriented compact 3-manifold, then the BPS, there are natural isomorphisms between the BPS cohomology for G and the dual group. And these conjectures are expected to be related using some stacky non-abelian force theory. So very heuristically, the point is that Higgs semi-stable G, it's comparable via non-abelian force theory with Loxis G on the Riemann surface, and then we take loop construction on both sides. So there are also versions, and maybe Safarov's initial version was for the full critical cohomology of the stack Loxis GM, but these versions, the version for the full stack or the version for BPS cohomology are related using this cohomological integrality theorem. And so of course, they are all conjectures, but one possible advantage of this BPS version is that this is an isomorphism between finite dimensional vector spaces. So one could presumably also try to compute dimensions on both sides. And this is also, kind of part, or at least Safarov's conjecture, and his direction is part of this Langlands duality for 3 manifolds studied by Ben-Zvi, Cunningham, Jordan, Safronov, following Kapustin and Wee. Okay, so this was everything about cohomology. So now we'll start the third section, quasi-BPS categories. So we said that when we the purpose of this lecture is we look at the stack of interest, for example, a stack of objects in a category we care about, and we want to look at the linearizations of the stack. And the first one was cohomology, and decompose that into some quantities that should further meaning. So they are related to this BPS invariant, and there are some kind of nice dualities that they should satisfy, as explained on the previous slide. But there are other linearizations one can use. Instead of cohomology, one can look at K-theory, or one can look at derived categories of coherent sheaves on the stack. So this is I'll focus on the last situation. But I should be saying right from the get-go that it will not be a perfect analogy between the results in cohomology and those in categories, and this will be explained, I hope, today. Also, but I should also be saying that the categorical versions do not imply the cohomological versions. just because from DG category, we extract two periodic version of cohomology in some situations, for example, from varieties. But yeah, so also the categorical results are not maybe as developed as those in cohomology, but there are new phenomena for categories. And here, one main difference is that in cohomology, there are possibly other approaches to BPS invariants and BPS cohomology, not necessarily the one I exposed before. So there are also this direction of Ziegler using p-adic integration at the numerical level. For the first two lectures, this was just one approach, but this approach is heavily based on perverse sheaves and uses the machinery of perverse sheaves in a fundamental way. But this is not available, at least at the same power, at the level of categories. So one has to find other methods actually to study categories, and a posteriori compare the constructions, the results with the ones in cohomology, because those are also sometimes computationally powerful. And as before, I'll first talk about smooth stack. So today I just talk about smooth stacks, and in the last talk I talked about -1 shifted, 0 shifted, and time dependence. So for smooth stacks, instead of singular cohomology, we'll study the derived category of bounded complexes of coherent sheaves on X, the same as the category of perfect complexes on X. And then a first difficulty arises when looking for the replacement of BPS cohomology. So for smooth stacks, the BPS cohomology was intersection cohomology. So we need to find a categorical replacement. In some sense, this kind of direction is at the beginning independent from the one in cohomology, and just later one compares the two approaches. So instead of using intersection cohomology and perverse sheaves, we'll be using what are called window categories. So this will be examples of quasi-BPS categories, and they will actually be the quasi-BPS categories for smooth stacks. And in this case, they are also called magic categories. So that is in the case of self-dual representation, so reductive group. So these window categories, they work for more general stack quotients, for example, just arbitrary quotient of a representation by a group G.
So Tudor, I mean, you're kind of too fast in getting, I mean, from the general perspective point of view. So far it was about some whatever good class of stacks, and then you studied constructible sheaves, because perverse sheaves, and whatever you've done, you use constructible sheaves on X. Yeah.
Yes.
Now you are saying, okay, I'm not going to use constructible, I will use well, coherent sheaves like perfect complexes. But what's how this story is related to the previous one in any way? You said that it's about cohomology or something. I didn't understand. Why whatever you say, you will say, is related to whatever you have said.
Yes. So the reason is that out of this DBX, out of the category of coherent sheaf, we can we can consider periodic cyclic homology.
When you say DBX, you mean constructible?
No, DB co.
Yeah.
Yeah, so if we consider the category DB co X, if we take its periodic cyclic homology, we recover two periodic version of the rank of homology of X.
Yeah, that's true, but the RAM is not quite cohomology coefficients in perverse sheaves, so it's...
No, Yes, this is true. But well, as a but okay, but also we are not actually studying um, all perverse sheaves. I mean, the coefficients are in certain sheaves. And initially, the certain sheaves are basically constant sheaf on a smooth stack. But yeah, okay. But
When you take cohomology and coefficients with a sheaf of vanishing cycles,
yes, yes,
it's not quite
yes,
constant, or at least if you say that in some sense it's constant, it's smooth along certain filtration, so you should kind of explain what
yes.
do you
But
mean. Because HP is just cohomology is coefficients in the constant sheaf. This is it. You cannot make it constructible, at least unless you do some extra work, which I
yes,
don't.
yes. But yeah. So maybe this is so. If we start with a smooth stack, then we don't care about vanishing cycle sheaf initially. So we just look at the constant sheaf
Mhm.
on X, right?
Right.
And then we look at summands of that cohomology along certain maps.
Uh,
These are right. So we look at QX and later summands of this good modular space. So in the smooth case, yeah, kind of the analogy of this constant sheaf is this dB co X. Because if X were a variety, then out of dB co X, we extract the rank cohomology of X.
the RAM
So
cohomology, yes, that's true. But something more sophisticated, like cohomology coefficients in the in some perverse sheaf,
yes,
it's more.
uh, but uh, but this is so in the smooth case we kind of we don't look at arbitrary perverse sheaves. We look either at the constant sheaf or at summands of this push forward.
Yeah, I mean, okay, maybe it's maybe it should be part of a later discussion, but there is something here, some phenomenon which kind of not you, but people do not discuss, because there are two types of whole algebras which sometimes give the same result. It's one is constructible whole algebras, and the other is cohomological whole algebra. So
Yes, yes, yes.
when you categorify,
Mhm.
uh, mm, I mean, the categorifications can be different. That's what I mean. Now you're talking about dB Koch of your stack, and you can talk about also motivic sheaves on your stack. So it's roughly the difference between uh, like, there are constructible functions and there are, I don't know, analytic functions on say complex manifold. So constructible appear according to Grothendieck as traces of Frobenius on analytic
Yes.
sheaves. Yeah, so then it's one story, but mm, uh, well, analytic they do not appear in that way, so they are rather related to what you denoted by DB Koch. So it's a bit kind of, we proved with Maxim that it's long ago that in terms of DT invariants, at least for quivers with potential, two approaches give the same result. Yeah, but somehow the whole algebras are totally different. So then I'm just This is why I'm asking you that you kind of easily switched from constructible to coherent, but it's maybe not that innocent change. Maybe there is
No,
something.
but I think, let me see if I understand. But you're kind of, maybe, so one way to rephrase your question is, why do I use dbco X and I don't use another categorification?
No, you are free to, it's a free country. You can use whatever category you like, but the question is about the relationship of two things. You develop some theory which is based on perfect complexes. This one story, great. But one can derive, and it certainly, even if X was a variety, it certainly depends on some complex structure on X. Anyway, in your
Yes.
case, but you can develop some topological theory looking for constructible sheaves on X. And so then it's something for example, you could easily define the perverse filtration in that in the constructible setup. But here, I don't know.
But,
It's rather Hodge filtration if you go to HP. So then, if you are interested in cohomology, yes. But if you're interested in
but
something more sophisticated,
But if
like
you consider a category of constructible sheaves, how do you extract singular cohomology effects in a global way? So I understand if you look at the category of constructible sheaves, there will be a specific complex. And then if you consider X and of that complex, you will recover.
yeah,
But kind of in a how can you do it in a global way?
I don't know. Like even if it's not a stack and a variety, how do I do it in global? I try to find, I don't know, spectral sequence or something, and then pray that it converges to global cohomology. In the smooth case, probably it's true. In non-smooth, you get more. Anyway, sorry. Yeah, I kind of diverted you from.
But I think another way is to think, okay, we do singular cohomology, and then let's say we want to do K-theory. Let's say we want to look at the K-theory of stacks, and then develop something about that, and try to prove this version of cohomological integrality and kind dependence. But then, if you do K-theory, I think that's very close
Yeah,
to
yeah,
just
yeah,
doing
yeah, yeah. That's the
dbco-X.
point. If you want to go to topological, you need kind of Chern character or something.
Yes, yes,
Yeah.
yes, yes,
Okay.
yes, yes.
Mm-hmm.
Yeah. Okay. I think I understand partially, and I think indeed it's not maybe you know. I think yeah, indeed there is some sort of jump here that maybe I don't understand completely, but this I think uh, in any case it's an interesting problem. So from a category of coherent sheaf, it's very natural to look at K-theory. One extracts naturally algebraic K-theory, and then using after blanks work also topological K-theory. But as I said, also this mod to periodic version of singular cohomology. But yeah, in any case, yeah. So what I want to say is that what I discuss are these categories are examples of window categories studied by these people. So Hori Roma, and Siegel based on Hori's first construction in physics, and then Telemann's work that precedes Hori's work. So I didn't write them chronologically. Balafaveru-Katsarkov, and many results that we'll be using are due to Halpern-Leissner. So now I decided to kind of give the full definition and yeah, explanation for this magic categories. So the example, i.e. quasi-BPS categories in the case of global quotient V mod G, where V is a self-dual G representation. And first I give definition, mention some results, and then I give a full example. So here it's some notation related to the reductive group G. So W will be the Weyl group. We consider weight space, co-weight spaces. And if chi is dominant, we let V chi to be the irreducible G representation of highest weight chi. And I use rho for half the sum of positive roots. So it's also okay to just think that G is abelian at the first go. Then some of these will simplify. So main construction here is of a certain polytope. So based on the group based on the group, we'll look in the R span of so we'll look in the weight space of this group. Then, based on the self-dual representation, we select a polytope that will tell us how many generators we will put in our quasi-BPS categories. And this is the first definition of this. So this is the kind of first go at this construction, is we consider Minkowski sum for all intervals 0 beta, where beta is a weight of the representation B, and take half of that. So we'll see explicit examples, and then I'll also comment on this trace later. So we'll consider all dominant weights high, such that chi plus rho minus delta is in this polytope. Yeah, so here I've said that delta is a Weyl invariant weight. So this will be a new phenomenon that appears for categories or in K theory. That the definition, that some of the construction will depend on extra parameter delta, and will be free to move delta around in the weight space. And so initially, it's not obvious that the categories are independent of delta, at least if delta is generic, if it's not on a wall, but it is true. So we'll also obtain some autoequivalences of these categories. So the category that we'll be using to decompose the stack in itself and some parts that come from parabolic induction is this category M delta, which is the full subcategory generated by this equivariant vector bundles, where chi is a dominant weight in this given set in the interior of this polytope. Okay, so this is the combinatorial description.
The polytope is non-compact or what?
It is compact.
It is compact.
Yes, yes,
okay.
Yes. Okay,
I guess a quick question about the delta, small delta.
Yes.
So those are just the characters in the center of the reductive group. Am I right?
Yes, yes, yes.
Okay. Okay.
Okay. Yeah, so this is our first go. Let's we can also describe this construction in some other way. So when studying stacks, it is an approach is to look at maps from the stack BGM into X and kind of characterize different constructions in terms of these maps. So why is this? Because a map from point mod GM will correspond to picking a close point. So we send the point to a close point, lowercase x in our stack, and the group GM maps to the stabilizer group of X. So this is this formation. So it's a useful construction to kind of keep track of all the stackiness of all the non-trivial stabilizers. Okay. And the plan will be to pull back complexes from X to BGM and impose some weight conditions there. Okay. So we can take pullback because X is smooth. And once we go to BGM, we want to say something about this category. And the category of coherent sheaves on BGM is the category of representations of GM. So they split in terms of one-dimensional representations of GM, on which GM acts with weight W, where W is an integer. So any complex in DBCO BGM, E will split as a direct sum in summons EW, where W is an integer. And then we define the set of weights, which are those W's for which EW is different from 0. And then here I'm also introducing some notation about the cotangent complex. So we'll pull it back to BGM, and then the less than 0 part will be the direct sum of W weight part of the cotangent complex where W is less than 0, and similarly for greater than 0. Okay. So now using this this type of maps, we can characterize quasi-BPS categories as, or magic categories, as the full subcategory of DBX containing complexes F such that for every map lambda BGM into X, when we pull back, we have a very explicit weight condition. So the weights will be in an interval depending on lambda. So this interval is half of something, so we can move this half, if you prefer, in the cotangent complex and say square root of the cotangent complex, or leave it like that, so I don't have a preference. So it will go from the determinant of the lambda less than 0 part of the cotangent to the determinant of lambda greater than 0 part of the cotangent, and 1/2. Okay. And how does delta appear? Delta appears by moving the interval. So what will happen is if both endpoints of the interval are integers, this category will be slightly larger. Okay, so it will be slightly larger. We'll have because we'll allow one more weight than when the endpoints are not integers. And kind of as a first go, heuristically, it's actually true if the group is just GM. The case in which these endpoints are not integers will correspond to the BPS case. We'll construct categories that will recover BPS invariants. But when they hit integers at the endpoints, it will correspond to quasi-BPS.
So it's a definition, it's pretty formal. So what actually does it mean? So you work with DB Koch, not with perfect complexes, all right?
But it's the same. It's same because X is smooth.
Your stack is smooth. Yeah, I forgot. Yeah, but anyway, you want some kind of, I don't know, stratification or something, because you put sheaves in different strata depending on how they behave at one parameter subgroups of the stabilizers of points. But either except of this pretty formal definition, is it possible to explain kind of in a simple example what's going on? I don't know if I take what kind of stack. What are coherent sheaves on a point mod GM? Yeah.
Okay. I'll do examples in a second.
All right. Okay.
I think indeed this is also a true comment. I think the definition is it's not clear why this works, but okay. I have 20 minutes. Okay, so I'll do examples.
Go ahead.
But no. It's just okay. I want to example, but I also have a comment maybe about why we also keep quasi-BPS and not only BPS. But yeah, but I should say that this definition above doesn't use now the stack just V mod G. It applies automatically if X is a smooth stack. And then ta is now our linear line bundle on X. Okay. Yeah, I think maybe. Yeah, so maybe I should just briefly say, so kind of what is the idea of these theorems, and then I'll do examples. I think maybe this will clarify many things. So what we want to do is to find semiorthogonal decompositions now. So instead of, I mean, so in cohomology, one use BBDG decomposition theorem. Okay, of course, this is not available here. So what we'll do is look for semi-orthogonal decompositions of our category dBx in this categories of generators together with parabolic induction. And okay, so this is kind of vague right now. It should be, yeah, it should be somehow analogous to the same in the cohomology. And also this semi-orthogonal decomposition should be in pieces as fine as possible. So if we can divide further one of the summands using the whole product, we should do that.
What is face of X? X.
Yeah, so this is kind of one of these things I did not explain. So this is the statement for general stacks, but so this phase has to do with the connected components of the mapping stack from BGM onto X. But in like all examples we look at, this just means that Z, what will happen is our stack is dependent on a reductive group G, and Z is the corresponding stack for the Levy.
Since it's semi-orthogonal decomposition, homes in one direction should be zero, and what in
Yes.
what direction?
Yes. Okay. Maybe I'll do this example now. Yeah. So let me do GLD plus L mod GLD. So this is kind of the example we discussed yesterday. So it's the stack of representations of the L loop quiver. So first, it has an orthogonal decomposition in subcategories in which, yeah, so what happened in cohomology is that we kept carrying this cohomology of BGM with us. So that GM appeared as the diagonal GM in GLD that acted trivially on the Algerian representation. So in K-theory or for these derived categories, this appears as this W here. So these are the, yeah, we will not see this cohomology of BGM anymore, but we will see these decompositions in weights W. And actually, these categories will be different depending on the W. So there will be the categories of sheaves on which GM acts with weight W. So how do we study this category? We consider Levy, consider Levy and parabolic subgroups of GLD as follows. So I also wrote this here. And then we consider the maps between this stack. So we consider partition di of D, and then we take the stack of representations of the L loop quiver for dimensions D1 up to dk, this part. Then we look at the corresponding stack of extensions. There is a map Q, which is smooth. And then there is a map a proper map to the full stack of representations. So this is the diagram used to define the whole product, which is denoted by star, and it's Q pull back by Q and push forward. So it induces, this whole product. Okay, so kind of now let me make a more explicit statement than on the previous slide. In this particular case, The theorem says that there is a semiorthogonal decomposition of this category. The summands will all be whole products of these categories of generators I specified, MDI, WI. And now I have to...
This whole product,
on the
is
next
it, I mean, you call it product, yeah? So is it
Yes.
kind of sort of a tensor product, or what it's
Uh,
convolution?
It's a whole product.
I don't know what is whole. If you deal with categories, I don't know. You have some bilinear or polylinear operation on categories. So there is something on category, there is tensor structure. I mean, that's terminology, it's different. Product, it's for algebras. For categories, it's tensor product. So I'm just asking what...
It's okay. It's the product between two DG categories.
Yeah, but is it, I don't know, associative? I mean, it's serious thing if you have kind of on two category of categories or whatever, you have some tensor product type structure, it can have consequences for...
Yes. So I skipped this, but so here it's the product of two DG categories, and then this will be a functor between these two categories, and one shows it's associative.
Strictly associative, yeah?
Yes.
Okay.
Well, this is a type of parabolic induction called whole product that gives a multilinear functor.
Yeah. It's multilinear, polylinear. Yeah, okay.
Yeah, because here if you take k equals 2, so that would be the binary tensor products. That's a whole tensor product, I would say.
Yeah, you see people kind of when they're dealing with higher categorical things, they use some terminology like, EN algebras and that stuff of things. Or EN categories, it's Luri type of terminology. Or whatever. So now you are dealing it with infinity categories in which yours sits inside. So then that's why I ask.
I do have a question here. This MDI with WI.
Yes.
So this, in the constructible sense, is this just the direct images? What is this MD? Is the direct image of the constant sheaf on this, or?
Well, I think that would be a posteriori. So
I see.
I think roughly. So you mean MDIWI or just MDW?
Yeah, FDIWI for each of those components.
Yeah. So this will correspond in in cohomology. This was some product between BPS of XDI. Yeah. So this W does not appear. Well, or if you want it, I mean, let's say it appears here when we put a polynomial in one variable, and then we take this product from I equals 1 to k. So this was a direct summand.
It's a direct summand.
In the symmetric algebra.
Okay.
So we had the symmetric algebra on direct sum of BPS.
You mean your MDI is a direct summand or what? Because I didn't understand what MDI is. Simply. What is it?
I mean, MDW is the category I defined before for this stack DBXDW.
Should I remember? And how did you define it before?
That was
so
quick.
okay, so it's this category.
Okay.
So for any stack, we
Yeah,
consider
okay, some conditions on the weights.
And
yes,
the weights on the in this framed box, so that is the interval
yes,
of the integers. Am I right?
yes, yes.
And the determinants, when we pull back by lambda, that gives
Yes.
you, I mean, it's a direct sum of okay. So when you write that as a determinant, so I guess you take the highest wedge power, and then to see what the weight is, that will give what the determinant. Am I right? Trying to understand.
Well, so yeah, what I mean, this
Yeah,
yeah, so
that is kind of a great direct sum of direct sum copies of the representations for the GM.
Yeah, so it's a difference of two representations of GM.
Yeah.
So for each of them, we take yeah, it's something like that, W, and then we take the dimension,
and then just do.
And then we take W.
Mm-hmm. Okay, so that yeah. So that's what we would call that character, but so you use the determinant that yes, that's
okay. Yeah, so okay, so yeah, so this is this category M in this case. So so this category MDI will be the category corresponding to dimension DI instead of D. Yeah, so maybe just to answer this question, so the order will be, so yeah, so here we have kind of this combinatorial description of the summands, but yeah, so they will depend on partitions of dW, and there will be a certain slope condition on them that yeah, the slopes are increasing. And the summands are in a bijection to paths from the origin to dW, and the order will correspond to the order on such convex paths. Yeah, so kind of again spelling out the definition of MD in this particular case. Yeah, so beta 1 up to beta D are the weights of the standard representation. And then a weight chi is dominant if CD is greater or equal than C1. And this category MDW, so yeah, I'm now just repeating the definition in this particular case, kind of the first definition that I gave. It will be generated by some equivariant vector bundles for dominant weights chi that satisfy a condition. So chi plus rho minus the delta, and there is only one delta now, while invariant weight that will correspond to our W in Z, which is this one, has to yeah, be a lattice point inside inside this polytope. So what is happening if L equals 0? Actually, all this, yeah, so one has to check this combinatorial condition. So if it is easy to see, these categories will be empty unless the dimension is 1. And then the categories will be equivalent to dB of point. And when L is 1, so we look at the representations of the Jordan quiver. Again, it's some combinatorial question. And then these categories are empty unless D divides the weight W. And then there will be only one chi that satisfies this inequality, which is W over D times the sum of the weights beta D up to beta 1. And one can explicitly describe this category. So MDW will be equivalent to MD0, and they will be equivalent to dBco of the good moduli space. And this is one of these very rare situations in which the good moduli space is smooth, is AB. So these are some explicit description, and one can put them in the semi-orthogonal decomposition and get explicit description of this category. Yes, but what happens if the number of loops is greater or equal than 2? Then, yeah, the definition of MDW is just what I wrote before. It's harder to simplify it. So it's just a category generated by some specific lattice point. In particular, it's not known to me, and yeah, I don't see any reason why it will be equivalent to dBco of a variety. So it's not geometric. Yeah, so here I'm just, I mentioned a comment about maybe this comparison with Coha. So in the PBW theorem for Coha, this cohomological integrality theorem says that Coha has the same size as a symmetric algebra on this BPS cohomology of each dimension D of our quiver times this cohomology of BGM. One might ask for a similar PBW theorem in the K-theoretic whole algebra case. So the K-theoretic whole algebra is you consider this whole product I wrote here, but at the level of locality groups. Then it is associative. So the best case scenario would be that the KH is isomorphic as graded vector space to a symmetric algebra on some K-theoretic BPS spaces times K0 of BGM. And we have partial results, and we actually proved this in some for some quivers, and also for some quivers with potential. But one way to write this isomorphism is that the KH is isomorphic to, yeah, we can decompose it in terms of slopes. So the slopes will come from ratio of a weight W and a dimension D. So the weight W is the power of Q that appears here. So it will be product after slopes of certain symmetric algebras that are smaller than the symmetric algebra I wrote above. And actually, these algebras, these symmetric algebras, okay, so this is the expectation in K-theory. One might ask, is a similar expectation can one hope for something similar at the level of categories? And yeah, the answer is no. So for categories, we cannot split further this symmetric part. So this symmetric part, when we write it just as a graded sum after dimensions, it will be the K-theory of this quasi-BPS categories I'll discuss. So far, I just discussed the smooth case, this MD delta case. So what will happen is if W is coprime to D, so it's a primitive a pair, then the categories will recover BPS invariants, but they will not in general. And there will be this phenomena that quasi-BPS categories will also admit products from certain partitions. So because heuristically in their definition, there was an interval involved, and if there are too many integers that we allow in the interval, that is, if the interval has both endpoints integers, then that will allow us for a whole product. to lie inside the category. So another way of saying all of this is as follows. We have a whole, this categorical whole algebra, which is individual pieces are dbco of sheaves on the stack xd, and we also have this extra weight, w. And when taking key theory, these are have same size as symmetric algebra on affine BPS algebra. So yeah, before taking anyway, so as algebra, they should be some sort of quantum affine algebra. But if we look at just these quasi-BPS categories, MDW, then if we take a direct sum after all pairs with a fixed slope, then we get a submonoidal category. So this was it's not a phenomenon in cohomology.
Submonoidal with respect to what tensor product?
The whole product.
Okay.
Yeah. And these will have the same size as symmetric algebra on just a sub-Lie algebra of the BPS Lie algebra. So the difference is that it's not affine anymore. And if mu, the slope is 0, this is just symmetric on BPS Lie algebra. So I say that, maybe kind of, a natural question in the beginning is why one has this quasi-BPS categories. Why aren't all categories considered BPS? And then, some categories cannot be split further, but this is not bad news. I think they are natural, and they also provide natural monoidal subcategories that are also interesting. So they will be symmetric on just BPS Lie algebra without definization. So they are more similar to the first categorification one considers for quantum groups. That is, for the usual whole algebras, one may look at categorification using perverse sheaves or coherent D modules. And those have this size, just symmetric on your Kac-Moody algebra. This work of Ringel, Lustig, and so on.
Listen, first, probably it's time to kind of start to stop. And second, I'm confused. Did you give a definition of a quasi-BPS category?
So it's just this category MDW.
Okay, so it's MD. All right. So the purpose main purpose is to have the semiorthogonal decompositions, and somehow stability in the form of slopes appeared, but if your stack was a stack of objects of some category, it's not clear, at least for me, how a choice of stability on the category is related to what you're explaining. So it's kind of
stability on the category or the
like you start, I don't know, like start with a category of representations of quiver with potential, choose stability, and that category king stability.
Yes.
So there is, you see, there's BPS, it's in physics and partially in mathematics, it's related to counting of stable objects on some category in the end, so then BPS invariants, blah, blah, blah.
Yes.
And these, it's not clear in this abstract. I would say too abstract. Language, how the stability on the category is converted into these weights and slopes. This, it's not clear. At least for me, maybe it's kind of written somewhere, maybe in Halpern-Leistner papers
But
or
it
some.
is true. Indeed, it is true that these categories are defined if you consider a stability condition in your initial category, in your abelian category, and the stack of semi-stable object. We are in the situation in which semi-stable equals stable. Sorry, the categories I defined is MD delta for delta generic will be equivalent to dBco of semi-stable.
Yeah, but another sort of conceptual question. So typically, like the level of algebras, these cohas for different cohomology theories, they depended on the stack of objects of an abelian category when you choose a T
Yes.
structure. Okay, great. Then the choice of stability on that category, like central charge, gives you this BPS type decomposition because of the Harder-Narasimhan filtration. Your stacks, they are not full stacks of objects. From the very beginning, you work with stacks of semi-stable objects. And so then the full stack of all objects, it looks like it does not appear in your story at all. So then your BPS decomposition, I'm even a bit confused what it corresponds on the categorical level. Because in that case, you have this Harder-Narasimhan filtration,
Yes.
blah, 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 and these decompositions, they correspond in the end to the decomposition and the Harder-Narasimhan filtration of your objects. And so then you can split them according to this Harder-Narasimhan type. But in your story, it's different.
No, I mean, we can also do that. But so it depends on what stability condition you choose. If you choose zero stability condition, then you just work with the stack of full objects in an abelian category, and you apply this mechanism, you construct this quasi-BPS category.
No. If I choose zero stability, then I will, yeah, but it's do you have a result for different stability conditions?
Yes.
And
Yes. For
what is
different
it?
stability.
That if I start with zero, I get full stack of objects.
Yes,
Great.
and then that has a semiorthogonal decomposition. If you choose another stability condition different from zero, you have a different stability condition that's compatible with the first one via restriction. But also for the first one, you can just produce semiorthogonal decomposition in the other pieces are coming from unstable loci that also have a description.
No, I do not understand, because for me, roughly speaking, you have the space of stability conditions, and you have the full stack, full algebra, full category associated with the stack, which does not depend on the point of this space. But a choice of a point gives you a specific semiorthogonal, whatever, wall crossing structure in our terminology. Categorically, it's semiorthogonal. Yeah, but in order to prove that the semiorthogonal decomposition doesn't depend on the point, you need some kind of wall crossing result that going across the wall, you have some quite non-trivial change of generators in the categories on the left and on the right of the wall. So basically, it's two different semi-orthogonal decompositions.
Yes, that's right. Yes.
And so then my question is, if I start with trivial stability condition and then I will move along the space of other stability conditions on the category, how it's reflected in your semiorthogonal, do you have a result that no matter what stability you choose, you get your semiorthogonal decomposition gives you the same category or what? So I'm kind of lost. But maybe, you see, maybe it's not a good time for discussion because our time is limited today. Maybe tomorrow we will have maybe more time because it will be your last lecture. Yeah. Also, I noticed that not everything which on the notes which you send me, I mean, you have more on your notes here.
Yes. So
Yeah,
I'll
so
send you
yeah,
updated
so
copy.
send me this updated
Yeah.
version, please. All right. Well, thank you, and we'll continue tomorrow. Yeah.
Okay.
All right. Thank you, and bye.